Thank you. Thank you so much for the kind introduction. You didn't forget anything, I think. I need to, before I get going and talk about some of the projects that we did in the past 2 years, I need a confirmation that you can hear me okay. That's good. And I need to tell you that for a number of years, I haven't been nervous anymore before giving a presentation, but today is a little different because I'm giving this presentation while my 2 kids are in the neighboring room and watching a film, because we had planned to have a babysitter to take care of them this afternoon. And then she got COVID and she's still positive. So they're watching an afternoon movie now, and I hope that that I will, I'll finish the talk and I will not be interrupted. But if I am interrupted, I'm sure that everyone in the audience will forgive me, because every one of us has been in situations like this one in the past 2 years, I'm sure.
We will not give you, we will understand your situation.
Yes.
We are even more thankful that you made it happen.
Yeah, and so as you can see in the background, I'm in my son's room, and so I can hear them with one ear. So I'm going to give you a little bit of an overview of the let's say digital epidemiology projects that we have been doing at Humboldt, and especially at the Robert Koch Institute, that involve large data sets. And one of them that is particularly dear to my heart is the data donation project, which I'll be talking about today. And if you're interested, you can go to that URL that you see on this slide. I can also post it later if you're interested in more detail. Now I have to see. Okay, but before I get going, I want to mention that the team that is behind all this work that I'm going to talk about, this is my team, and everyone is essential for the work that we did. And I'm going to start with this little screenshot of an animation that you will also find on our website, which is just a sort of a bird's eye perspective on COVID. And it's just a sort of a temporal snapshot. I don't know what the date was, but if you watch this video online or this animation, you will see that the global spread, the dynamics of this is actually very complex. It's very complicated. It's not like a wave that kind of traveled across the globe and then it's over, but there's a lot of dynamics in it. And the reason for this is, and you can also see it like in this little cartoon, we remember that in Germany we had these waves, the first wave and the second wave and the third and the fourth wave, and all of this up and down makes the whole dynamics very complex. And the reason behind this is not that there's like things that are changing to the virus. That also happens, of course. There are new variants always, like the last Omicron wave. But what this dynamics is dominated by is this feedback between the spreading of the virus, the transmission dynamics, and our reaction to it. So in order to understand what's happening, we really have to understand what the host is doing. And a little bit in the discussion and the scientific discourse about the pandemic, there was a lot of focus on the virus, and which is obvious because it's a viral disease. But it's also, the dominant factor is the host, us, our contacts, our behavior, our risk perception, etc., that feeds back on the dynamics of the disease. So most of what we're doing is trying to understand and quantify with new technologies host behavior. And here's a little illustration again of this, a little bit more complicated. So you may expect that there's some disease dynamics happening, transmission dynamics governed by like the reproduction rates and recovery rates and particulars of the disease. But then there's information on the pandemic, which generates psychological processes, which are poorly understood, the way we perceive risk and reactance and trust in the government, etc., which has an impact on our behavior, which then has an impact on how the disease spreads. And this kind of feedback loop is quite poorly understood actually, and especially because there's little data on behavioral factors. And then of course there's policy in the center of it, which is extremely poorly understood. So I'm going to talk about three projects. One is the mobility monitor. I'm not going to focus on this, maybe touch upon it in the last part of the talk, which we set up during the pandemic. The other one is the contact monitor, which is a way of measuring, quantifying the number of contacts, direct sort of proximity contacts, that as a function of time on a daily basis, which we used a lot to understand how the population reacted, for instance, to increasing case counts, etc. But the last one is the data donation project. And so I'm going to focus on this project because there are many, because it generated the most open questions. So it was there actually as a tool to understand the dynamics of the disease better, but with any exploratory and experimental new kind of approach, when you start analyzing data, you generate more questions than you answer. And so let me give you a little bit of an overview of what this data donation project is. Most of the things that I'll be talking about today are based on this instrument that almost every one of us carries around. So, it's our cell phone and the smartphone. It has lots of sensors and it gathers lots of information, which we can use in order to quantify behavior. So almost all the projects are based on things that are attached either to the cell phone or apps that have been installed on the cell phone in a sort of citizen science project. And the data donation project is based on wearable devices or fitness tracking devices, smartwatches, fitness tracking devices that record physiological data, like the step count every day, or the resting heart rate, or sleeping patterns. And so this is, I apologize that this slide is in German because it's an app that only runs in Germany. Now my daughter has called. Just 1 second. Ja? Was denn? Frag mal Karlchen. I apologize. See, now it's starting already. 5 minutes into the talk.
No problem.
Anyway, yeah. So the idea behind this is to develop an app that would take the data that is collected by the manufacturers of these instruments and enable people to donate the data that is collected by these companies anyway, and then use the data in order to get a better idea of the impact of COVID. Because if you get COVID, like any other disease that generates a fever, for instance, it will show up in your physiological data. So that's the basic idea. And it's a fairly new idea, but also not that new. In early 2020, a paper was published by people at Scripps, Eric DePaul, Steve Steinhubel, that showed that you can, if you have a large population of people that wear wearable devices, on a population scale, you can see if there are local outbreaks of influenza, for instance, because a more than baseline fraction of the population will develop fever, which will show up on these devices. So here's a little time series of our data donation project. This is 2 people that we monitored over a long period on a daily basis. And in the top trace, you see the resting heart rate, and you see there's some sort of baseline and some variability. The same is true for the physical activity and for the sleep duration. And if you focus on the left trace, you can see that there's a gray area, a gray bar. And the person developed COVID in that time period. You can kind of see that there are 3 generic things that happen. People have an increase in that resting heart rate. They have less physical activity because they're either sick and stay at home, or they isolate themselves, and there's a larger need for sleep. And so it never, it's not like that this occurs for every person, but it is more likely. So if you have a large population and you see that this happens more frequently than you would expect, then you get an idea of the dynamics, and you can measure this every day, and you don't have to use the complicated reporting system, but you see it immediately in the data. That was the basic idea. And so we started this in April 2020, and we have very quickly, we had like 500,000 donors. At the moment, there are about 180,000 active and about 120,000 that have donated more than 600 days of data. And I'll come to this later. We also started the second version of this where we can actually talk to the people. We can run surveys. So having an interaction and gather more information. But that only started in October last year. And about 38,000 people are participating in these surveys, and talk about this in a bit. And at the moment, this is the largest wearable sensor data donation project worldwide, and we're just beginning to understand what we can read out of this data. And so I'll just give you a few examples. So one of the things that we did early on, we had to really get a feeling of, what this data looks like. So the first map that we produced, like 2 weeks after we launched it, is the number of donors as a function of location. And it's not uniform. And, it's more popular in West Germany. It's less popular in East Germany, except for in Berlin and the largest cities. This is the sort of sanity check stuff that you have to do if you look at data that you haven't seen before. But it's important to keep in mind. Or, here just a few things. There are more women that participate. The age distribution is quite different from what the age distribution is in the population, because it's usually sort of in the mid-age ranges. People use it more than you would expect from the population, this age distribution. And this is sort of age and gender. It's a little different between men and women. So these are the sort of things we did in the very beginning. One of the things that puzzled us also in the first month or so after we did this is that we computed the resting heart rate per county in Germany. And there are clear, significant differences. And this is not sort of because of noise in the data, because there are lots of people per county. And there's more information on the blog that we do, but we published this, and then everyone was like, why is this? And the fact is we don't know, and but it is significant. So in the eastern part of Germany, the resting heart rate is larger, and it does not mean, and despite the fact that the age distribution is very similar. So we don't know why this is. So this is one of the open questions that we haven't had time to look into yet. Likewise, for the daily step count, there are sort of areas where people walk more. We don't know this yet, why this is. But now let me come to what we really wanted to do with this data. Like I mentioned earlier, the idea is that when people develop a fever, and this is based on this paper that I mentioned earlier, what happens usually is that the resting heart rate rises and the activity goes down. Sometimes the resting heart rate goes up and activity goes down. This is often due to people doing sports, or they're on a bike holiday or something like this. But when resting heart rate goes up and activity goes down, it's more likely that you have detected a fever situation. And there's a large number of false positives and false negatives in this, but if you have a very large population and you see deviations from sort of the usual baseline, you can potentially mimic or monitor the case counts as a function of time. And so this was what we first did, and you can see here in the first year the COVID curves and our detections in blue, and it followed very nicely the incidence curve. And so the idea was to have a system that is much faster and better than the reporting, which usually has a even longer week delay, and all sorts of other errors that are part of the reporting system. So that was the idea. This was actually quite hard because there are a number of factors that you have to account for, like weather and climatic changes and holidays, etc. So it turned out to be a lot harder than we expected. But we ended up developing a nowcast system that incorporates this this method, and it is much better than the nowcast that was previously used, and it's still running. So the whole machinery of collecting this data on a daily basis, pre-processing the data, getting rid of errors, managing the data, doing the algorithms, etc. All of this is done every day, and then there's a point that is computed every day, and we publish it every day. And that's the current nowcast based on the data donation project. And now here are a few things that we haven't looked at yet. One of the things that we did, because we have such long data streams, is we ask ourselves, so what's the difference between 2020, the first year of the pandemic, and 2021? And we found, for instance, the resting heart rate is substantially larger in 2021 in all of the federal states, and that's significant. And we don't know why this is. There are various theories. It could be that people gained weight. It could be that people are more depressed. It could be that people are more tired, or they behave in a different way. But it's systematic, and it's like this in all the states. We haven't looked into it yet. We don't know. So it's like an open question that came out of this data. Likewise for the sleep duration. So sleep, people slept longer in 2020 than in 2021. We also don't know if this is stress related, if it is, we don't know the factors. There are various theories, but we haven't looked into it yet because simply we haven't had enough time. The kind of message I want to convey is that we have this data and there's so many open questions because we have these long time series of physiological data. And so we only had time to look at it superficially. I can skip this. Sleep is an interesting part. Here we have a project where we dive a little deeper into this. What you see here is a map of sleep in Germany. And what you see color-coded is the mid-sleep, which is kind of sort of the mean of when you go to bed and when you get up. And so it's the middle of your sleeping period. And you can see it kind of shifts from blue to red if you go from east to west. The reason for this, and this is known in the sleep community, is the sun. The sun sets and rises at different times from east to west. That's known, but there are interesting exceptions. So what you can do is you can account for the sunrise and sunset. And you can see already in this map, for instance, if you look at Berlin or the larger cities in the east, they look a little bit more like the west. And this is also a known result that in urban areas, if you just focus on one of the graphs, there are two slopes of the solid lines. One is the purple slope and one is the black slope. And the smaller the slope, the less you're getting up or going to bed depends on the longitude of where you are. So depends, the smaller the slope, the less the sun plays a role in your timing. And you can see in the sort of countryside, the slope is larger. So there's a larger impact of sun than if you live in the city, which is related to, the sun, if you live in Berlin, plays no role essentially because everything is bright. And this is a known result, but the last time this result was obtained was a few years ago by a massive survey, a huge undertaking of surveying thousands of people scattered in the United States and looking at this and measuring when they go to bed and when they go up, and they have to report it and record it, and you have to digitize it. And so here it's just sort of a day of analysis, essentially. And so we're currently looking at this and in more detail to see, how, light pollution impacts our physiological data. Now, I mentioned that in October last year, we made a little add-on to the data donation project. Up until then, it was a passive tracking system. Because of the data protection agencies, we were not allowed to interact with the donors. So they installed the app and they donated their data. We had no means of contacting them or sending them push notifications, etc. But this interaction makes it a lot more fun. So initially, when we started with 500,000 people, slowly it trickled down because people like Apple users, when they didn't use their app for a longer period of time, it just deactivated essentially. And so it took a lot of convincing and discussions with the federal data protection agencies to convince them that it's a good idea in this data donation citizen science project to interact with the donors and to ask them questions. And so we launched the data donation project in the next version in October last year. And we have the machinery to run surveys. And so there is the first survey is just the monitoring of the physiological data, but we now can ask, did you have COVID? Did you get tested? If so, what were your symptoms, etc. And when we release such a survey, usually they're very short and people can sort of answer the questions when they're sitting in the subway. It's very sort of low threshold surveys, but the numbers are large. And the way we set it up is that now also external partners can devise surveys and we just integrate it and then run it to, the 200,000 people that have a chance of participating. Also, since very recently you don't have to have a wearable device anymore, so we can run surveys also for those people that don't want to wear a tracking device and just want to answer surveys. So it's a very sort of it's a powerful technology. And this is what a survey looks like. You have a few questions. You don't have to answer all of them. They're very simple, unlike sort of the traditional panel approach. And so one of the things that we did is we asked the people, when did you have COVID? When did you have a positive PCR test? And just to pinpoint the location and time when they did have COVID. And one of the things that we found is with this information, being able to actually pinpoint the point in time, here illustrated by a vertical dashed line, there's a little bit of uncertainty about a week around this because of data protection. Because of data protection, we were only allowed to ask for the week where they had a positive PCR test. And so you can see that in the top left, you can see in red those that have had a positive COVID test and their heart rate response averaged over that population. So that's the solid red line. So it's a population, and on average, the heart rate went up. Is that heart rate? No, it's sleep duration. I'm sorry, sleep duration. I was a little confused. So the sleep duration for 20 days, for like 3 weeks, was above average. Likewise, the activity went down. That's compared to the blue line, which is the negative PCR test baseline, the comparison, the cohort that didn't have a positive test. But what's essential is the figure on the bottom. That's the absolute change in resting heart rate. And you can see right around the PCR test, the heart rate rises on average, then it goes down, and then it rises again about 3 weeks. And then there's a long tail that it takes up to like 80 days on average. And remember that this is sort of not a representative cohort. These are people that have fitness trackers, usually very fitness aware. We have, like, in the community of donors, 99.5% are vaccinated, usually young people. And you can see this little dip in the resting heart rate. And this has been measured before, not only in our study, but there's the Scripps Institute in California. They got exactly the same results. And those people that know about cardiology had an explanation for it. I can't remember what it was called, but it was very typical. But what's important is the tail. So on average, there is a substantial effect on your resting heart rate after a COVID infection. And in the next paper, what we did is we differentiated people that were vaccinated and those that were not vaccinated. Like I said, those that had an opportunity to vaccinate in the cohort, they vaccinated all, but there were lots of infections also prior to the availability of the vaccine. So we do have people that had a positive PCR test without having been vaccinated. And when you compare this, and you have to be a little careful because you have to differentiate between the different variants, you can see if you focus on the top left, this is again the change in resting heart rate. The red curve is the one that I just showed you. These are the unvaccinated individuals that up to 12, 14 weeks after the infection still had an above average resting heart rate. And the purple are the ones that were vaccinated. So there are similar effects, but they're not so long, especially when it comes to resting heart rate. Also, the extreme cases, which are all the histograms on the right. So those people that are sort of in the tail of the distribution, so had a very high effect on the resting heart rate or on the reduced step count or on the increased sleep, are substantially higher in the unvaccinated compared to the vaccinated. So this was the first evidence that vaccination also has an impact on the likelihood of developing long COVID symptoms. And so here's again a little bit of a timeline of the history of the project, which I hope will continue. Initially, we had like the fever monitor and the complementary nowcast, and in October last year, we started the surveys, and this is really a game changer because we can now, based on what we find, ask individuals, also on an individual basis, on what they, whatever question comes to mind. And we just recently launched a very detailed long COVID study. It's a collaboration with University of Erfurt and Jena, and we just published our first preprint. It was a long journey, kind of. Because there's a lot of, I would say like 80% of this is engineering and, going into directions that don't work. And now I think it's the time that this can be really expanded and used. And one of the things is that was very important to me in the very beginning is that because it's a citizen science project and the donation project, people give us very personal information. We wanted to have a strong engagement of the public. So we started doing a blog from the very beginning. There are around about 25 reports on this blog. We try to update the donor community and the public. And, there are all of these intermediate results that we obtain, also sort of wrong things that we did that didn't work out. All of this is reported on this blog. And that's, I think, a very nice model for running something like this. The people that participate are very, very loyal. They do this for a long time, and they ask us, when do you have the next result? And my watch had an update. Now it doesn't work anymore. So they're very concerned that something goes wrong with their stuff. So it's also nice to experience this kind of doing good for the public in this project. And right now it has become kind of a network of collaborations because frankly, I don't know anything about sleep research. None of us do. And so we need to work with people that know about this. Or, I don't know how to set up a survey. So we need to work with people that know how to do this. Or I'm not a doctor and, a physician, I should say. And that knows about the cardiovascular system and about long COVID. So we work with those people. So it's really what I envision is really a collaborative project where people, develop ideas and then they can sort of use the data to answer their questions. And what I think is really in a nutshell, the benefit of this is because the wearable data accesses physiological data and the surveys sort of behavioral data or other information, and we can combine it. And usually these things have been looked at separately, especially like at the public health institutes, etc., where different scientists did the different things. And I think the combination is really promising here. And so that wraps up our activities on the data donation project. There's another project that we did, which is related to research that I did prior to this, and it's concerned with human mobility, which is also, of course, a proxy for behavior. One of the things that we set up is the COVID-19 mobility monitor, which is essentially based on cell phone, aggregated anonymized cell phone data, where we are given data on a daily basis, actually on an hourly basis, how many people go from one location, like one county, to another. And so you have like this network of like the flux of individuals between counties, and it changes as a function of time. And you know, it changes at night, and during the day it's different, obviously. But if you look at the different days, there are also other changes. And the cover that you see here on the left is the regular mobility network in Germany, and on the right is during the first lockdown. And if you look at this carefully, there is less intensity, but there's also a lot less long-range connections. And this is something that we wanted to investigate, to see how people react to the pandemic or to policies. So we set up this mobility monitor. You can go on the website and check it out yourself. And you can select different counties and see what the trace is. For instance, like this is a snapshot. I can't remember what time it was, but this must be a holiday because there's lots of above average mobility in the Northeast. So people are going on holiday. They don't fly anymore, so they do their vacation in Germany. So that's why there's usually in the summer of 2020 and 2021, there's a lot of above average mobility happening, because as compared to 2019, for instance. And so one of the things that we looked at more closely was during the first lockdown in March 2020, where really synchronously mobility went down massively. Here's a little bit of a trace of that. So there was the baseline, and then there were like these lockdown measures, the red vertical bars. These weren't actually lockdown measures, but you know, one of them was Merkel's speech that everyone should stop moving around, and a lot of things were unknown about the virus, and so mobility dropped by like 40%. But then interestingly, it went back up slowly. So there was a tendency for us to start behaving normally again, even before these release of lockdown measures were taken. And so we wrote a paper about this, and how also the network changed, and what kind of effect the network changes have on the speed on which like a hypothetical pandemic would spread through this network. And then finally, also an interesting project based on large scale data set is the contact monitor. I mean, obviously the pandemic is driven by contacts. And during the past 2 years, everyone was like guessing where all of these transmissions occur. But, you know, to be honest, we don't know that, right? Because we can't measure it. We don't know where contacts actually happen. We don't know where transmissions occur, except for in some cases. And so it's not a surprise that especially politicians, who always know what's happening, even though they don't, without any evidence, they have the answers. I mean, I was always like laughing when like some of the politicians said, there are no transmissions occurring at school, also X-rays, or there's no transmissions occurring in public transport, based on no data, essentially. And it was painful almost, but you know, if you experience a lot of pain, you get used to it. And but the truth is, we don't know, because we can't measure it. And one of the things that we did that's a little bit along sort of into this direction of measuring contacts quantitatively is not directed at where these contacts happen, but how often they occur. And so the contact monitor is also on this mobility page. It's a sub page of this, and it's essentially also using cell phones and data that is provided by a company that runs that evaluates positional data on an individual basis. We don't get it this way. We just get sort of the number of contacts and the distribution of contacts on a resolution of about 8 by 8 meters in a population which is about 1 million large. So you have to extrapolate to the entire population, but you get a rough estimate and a rough idea of what is changing. It's not really about measuring the absolute number of contacts, but rather how the number of contacts changes as a function of time. And so this is, for instance, two curves that we derived from this data. In green and in orange is the average number of contacts from early on 2020. You can see the lockdown, the massive decrease, and then kind of sort of an increase in the summer, and it kind of wobbles around in this low regime, and it's now picking up again and going back to normal. But what's essential is not really only the average, but the standard deviation, so the fluctuations in the number of contacts. And the fluctuations are with respect to the population, not with respect to time. So you can have a population that has, where everyone has the same number of contacts, producing some average, or you can have a population where a few have, or lots of people have few contacts and few people have lots of contacts, having the same kind of average. And it turns out for the disease dynamical properties, this kind of dispersion in the number of contacts is essential, which is kind of overlooked by classical models, but the heterogeneity in the contact networks really drives the pandemic more than the average contacts. And so when you look at the green curve, there are like these massive fluctuations that are occurring on the weekends, for instance. People behave differently. You can see it's different in the summertime or in the winter, and you can see how this is picking up again and getting to a normal level. And it's really the reduction not only of the average, but of the distribution that sort of pulled down the reproduction ratio. And so we've done this now. It's also evaluated daily for all the states. There are differences between the states, and you can also look at it closely and see, for instance, the impact if some states did some lockdown measures, and you can see immediately, what kind of effect that had on the number of contacts or the mobility. And so with this, I want to mention the team again. This is a great team. Lots of people that just basically stopped working on their PhD, which was on a different topic, and they just dove into some of these digital projects, and they did all the work. I'm just reporting it, and it's a great team. And now I need to advertise my book a little bit. So in case you want to buy a book about complexity, that appeared last year, and I kind of wanted to advertise it if you're interested in complex systems. So with that, I'm just going to start this slide again. And I thank everyone for your attention. And I took 45 minutes, and I'm getting a little nervous about the kids. Thank you so much.
Thank you very much, Professor Brockmann. We still have a couple of minutes time to